Okay, example sample problem 5.8. A simply supported steel beam is to carry the distributed and concentrated load shown, knowing that the allowable normal stress for the grade of steel to be used is 1160 megapascal. Select the white flange shape that should be used. Okay. So you maybe wants to develop the shear diagram and determine the maximum bending moment so that it will not be that it will not exceed the allowable shear stress, which is 160 MPa. So to solve this problem, first you have to so because the beam is like this, so it has force at A like this, and then it has B. This is point B, and then this is point C. It has 50 kilonewton at point C, and then it has D. FD is equal to, we don't know, and also this one also we don't know. So we have to find what is FA and FD. So like usual, we have to find either all forces in y directions and also the moment. So it should all equal to 0. So because this is the UDL, because this is a UDL, so this 20 kilonewton will act at this distance 3 kilo, or this one is actually 20 kilonewton over meter. So in 1 meter, this one should be 20 kilonewton over meter. So in 1 meter it has 20 kilonewton meter, but because it has 3 meter, so it is 20 times 3, so which is equal to 60 kilonewton meter. But this UDL is can act if we put that it in the middle, which is 60 kilonewton meter, which is 60 kilonewton meter acting in this 3 meter. So this one is half, so which is 1.5 meter, and this is also 1.5 meter. Okay, so moment, let's say we take moment at point A. So this should be equal to 0. Moment at point A, if we take this direction as positive, this 60 should be negative because it will go this way. If we take this one is positive, this one will be negative. So it is minus 60 times 1.5 and then minus 50 times 4. And then for D direction, it is going to this direction, so it is positive, plus FD times the distance is 5 meter equal to 0. So 5 FD is equal to 60 times 1.5 plus times 4, so you get this is equal to 290. So FD is equal to 58 kilonewton. So FD is equal to 58 kilonewton, and then summation of all forces in y direction is equal to 0. So you get, if you take this as a positive, so this is FA is positive and FD is positive, and then minus with 60 kilonewton, and then also minus with 50 kilonewton is equal to 0. So FD is equal to 58. Okay, you can change. So FA is equal to minus FD plus 60 plus 50. So minus 58 plus 60 plus 50. So you get this value is equal to 52 kilonewton. So this is equal to 52 kilonewton at FA. So when you construct the shear diagram, okay, this is the shear diagram. So this is 0, this is B, this is C, and this is D. Okay, so because it already have 52 kilonewton, so it will go 52 kilonewton here. Okay, and okay, 50 kilonewton here. Okay, but because this is a uniform distribution load, so uniform distribution load, the SFD, if this is UDL, so the SFD will become inclined either like this or like this. But because the UDL start from 52 kilonewton, and then gradually it will be decreasing because this one is 20 kilonewton over meter, so it will become decreasing. Okay, and at 3 after okay, so it will go down from 52 until 60 kilonewton because you get here in the middle, this one is 20 kilonewton over meter, is actually in 1 meter it is equal to 20 kilonewton. So in 3 meter it will be 60 kilonewton. So this 52 will go down until 60 kilonewton. So for the SFD, from point A to B, so at point A it will start with 52, and then from A to B it will go down from 52 to minus 60. So you get minus 8. So let's say this is minus 8. Ignore this line because I misdraw this lines by accident. So this is minus 8. So you get this line like this. Okay, and then because from B to C you have nothing, you have no force from B to C, so it will become from a point 2 from B to C. You have nothing, no forces, so the SFD becomes straight. So the FSD becomes straight like this. And then at point C you give 50 kilonewton. So you give 50 kilonewton here. So from B to C, because you give 50 kilonewton, so you have to add with the minus 8 plus with minus 50 kilonewton. So you get minus 58 kilonewton. So that's why this is minus 58. This is minus 58. So so it go down here. So but because from C to D, again from C to D, you have nothing, you have no forces acting from C to D, so it will, the SFD becomes straight line like this. Okay, and then finally you give 50, you give a 58 kilonewton here at FD, so it will become 0. Okay, because from C to D it is equal to minus 58 plus 58. It become to 0 because this one is FD. FD is equal to 58 kilonewton going upward. So you got this shear force diagram. Okay, so the maximum bending moment occur at V equal to 0 or at X equal to 2.6 meter. So the maximum bending moment, the maximum moment occur when V is equal to 0. Occur when V is equal to 0, which is here. So this is V equal to 0. So, and the distance of this is actually so if you draw this shear diagram on a graph paper, you can get actually this distance is 2.6 meter. 2.6 meter. So if you get this 2.6 meter, you can determine this value. So the value of this moment is 1 over 2 times base, which is 2.6, and then times height. Height is 52. So you get this is 67.6. So this value is 67.6. So that is the maximum bending moment. Okay, to find the value of minimum acceptable beam section modulus, which is S, so it is equal to, because the equation is stress is equal to M times C over I or M over S, so S is equal to M over shear. So this is 1 over S. So this is M over S, M over stress. So M is equal to 67.6 kilonewton meter. And then the allowable stress is given in the equation, which is 160 MPa. And then you get the value is 422.5 times 10 to the power of 3 mm cubic. So from this value, you find in the given table, so this value is actually close to this value. So that's why you choose this beam. Okay.